Great. So let's do our example of body temperature again to use the t-distribution to carry out a hypothesis test. And we call this a t-test because we're using the t-distribution. Excuse me, I am choking on some pecans. So I lost my voice momentarily. Okay. So remember that we started from the null and alternative hypotheses about 98.6 degrees. 98.6 degrees was the null hypothesis. That's the world that we wanted to simulate, and then we checked our sample result against our sample body temperature of 98.26. So we start with the same information. 98.6 is our null value. Our sample mean of 98.26 is our actual observed sample mean. And our sample standard deviation of 0.765 and a sample size of 50. Here's the beautiful thing about these theoretical formulas. It's plug and chug. It's super fast. We just plug in how far away the sample mean is from the null value, and then we divide by the formula for the standard error, and we get a t-score of negative 3.14. And what we can then say is, okay, if I have a t-score, which is, as you can tell here, a representation of how many standard deviations deviations away my difference from my null hypothesis I am, and I've got a sample size of 50 leading to a degrees of freedom of 49, I get the p-value by saying, well, how much of the t-distribution with 49 degrees of freedom is at or beyond plus or minus 3.14. Exact same ideas with the randomization distribution. Except we're starting with the theoretical distribution instead of simulating one. So if we go to our t-distribution with 49 degrees of freedom and we plug in negative 3.14, that gives us a two-tailed p-value of 0.0028 because there's 0.0014 in each tail. If we were to do the randomization distribution with this and randomize and center on our null of 98.6 and go to 98.26 down here, we get a two-tailed p-value of 0.00066. Okay. So they're a little bit different, but they give basically the same conclusion. And this is going to happen because this is a theoretical distribution and this is a simulated distribution. So there are going to be some differences that come out for a variety of reasons. The important thing here is that these conclusions agree, regardless of which method I used. Okay, so that's for a single mean. For a difference in means, it's still the same idea of taking my statistics, subtracting out my null value that I care about, and dividing by the standard error. It's just that our statistic and our standard error are a little bit more complicated. Our null hypothesis for any difference in means generally is that their difference in means is 0. The population mean difference is 0. The formula is, if you just pick this apart, should be pretty straightforward. This sample statistic is the difference in means here. The null value is 0. That's what we care about here, 0. And this is the formula from before to estimate the standard error for a difference in means. And again, to use this, we need both sample sizes to be greater than 30, or for both of the samples to look normally distributed. And then it's the same thing. We convert this difference to a t-score by finding out how much this difference minus the null value, how many multiples of the standard error it is, and that's our t-score. And we can get a p-value that the software will give us, fortunately. You will not have to do this. We will do this in StatCrunch, or R if you're using R, and we will see this in a second. And again, make sure you're using this assumption of unpooled variances. That just, for the math's sake going on behind the scenes, is a safer assumption to make. Okay, So let's do some examples here and show you how this works in StatCrunch. So to show you how you're actually going to use it. So using the example data.csv, let's ask a question. Let's show you what we got here. So I got some example data here of a bunch of students, 119 students. And we don't really know exactly where this is from. This is sort of just like, this might be real data. I'm not positive. It's just some example data to work with. We have some variables about students. Okay. So let's say we've got this age variable here of these students. And we want to ask, what's the average age of students in this population from which this sample came? Okay, so I've got a sample of students here, and I want to ask this question, what's the average age in the population? Well, what do we do with that? Well, since we don't have the population, we only have a sample, we need to build a confidence interval. We're not going to use the bootstrap distribution, though we can. We want to make this confidence interval using our t-interval, our t-distribution, and using that. Okay, how do I do this in StatCrunch? Well, I go under Stat, I'm doing a t-test here, and I'm only working with one sample right now. I'm not doing any comparisons, just one sample, and I'm using with my data. Okay, what do I care about here? Well, I'm looking into age. I'm not trying to pick anything specific yet. I just want the age variable. We'll do a hypothesis test in a second. Let's do a confidence interval, 95%, around what the average age in the population should be. I'm not going to add in any special tables. You can play around with those if you want. And I just hit compute. And bam! My 95% confidence interval, it just spits it out. It's 25.88 to 29.1. That's my 95% confidence interval using that t-distribution and those formulas just like we had before. It's just doing all of it for you. And this is what you're going to be doing on the activities and the labs, or the last lab, I guess, and the homework. Again, we got our sample mean here, 27.49. We got a standard error that's calculated. We got degrees of freedom here. And we have a lower and upper limit for what's happening. So that's it. That's the answer. So that answer to that first research question, we're 95% confident that the average age of students in this population is between 25.88 and 29.1 years. Okay, well, let's test something. Let's test whether or not the average age of students in this population is different from 30. Now, you might be able to guess that since 30 isn't in this interval, that there's probably going to be evidence that it's different than 30. But let me just show you how this works. So if I hypothesize that the average age of students in this population is 30, I've got a null value of 30, and I've got an alternative hypothesis of not equal to 30. Let's see, I'm just going to, for now, show you how to start this from scratch. So to do a hypothesis test, I do stat, I do t-stat, one sample with data, I care about age, and I'm doing a hypothesis test. Now the default is 0. We're not testing whether the average age is 0. We're testing whether or not the average age is 30. So I'm going to type in 30. I'm not going to add any, oh, actually, yes. I'm going to add in the p-value plot to show you that area under the curve here that we're going to get for this scenario. If I do that, bam, it gives me all my stuff. This is why people like the formulas generally, or why these things are used. This is why people do these sorts of things in software without simulation. When you know what's going on, it gives you everything up front and you can interpret it. So I get a t-statistic of negative 3.089. You could calculate that if you want. I get a p-value two-tailed of 0.0025. If I want to see what that looks like, here we go. Here's a t-distribution with 115 degrees of freedom, and I use my sample mean age to be converted to a t-statistic of negative 3.0892, which corresponds to a two-tailed p-value of 0.0025. And that's it. So that's a small p-value. It's less than our typical cutoff of 0.05, and so that we use that as evidence to reject the null hypothesis and find evidence that the average age of students in this population is different from 30 years. Again, same interpretations, same ideas. It's just we're getting at the p-value and we're getting at what our interval is using this t-distribution, which is pre-made by theory, central limit theorem, instead of constructing a simulation. Okay, in the last minutes here, let's do a difference in means test. And there's only one little tweak on this in StatCrunch. So let's say that we want to ask, what is the difference in average number of sleep hours between males and females in this population? So we want to estimate the size of this. We've got gender here, and we've got sleep hours. Now, here's an important thing. Gender is categorized here as a 1 for males and a 2 for females. So we've got some categorization going on here, but that's what that is. 1 is males, 2 is females. So if I want to make a confidence interval for my difference in means, now I am doing a mean difference, which means I'm working with, in a sense, 2 samples. So I'm still doing a t statistic thing. I'm still using the t-distribution, but now I'm working with 2 samples. And I'm still just working with the data here. Come on. So now I get to select what my 2 samples are for the comparison. Here's how this works. I care about sleep hours. That's what our research question is about. Now I need to tell it which group I want to pick. I'm picking a subset of this data. So if I want to pick just men, then what I do is I put in this little logic statement. If I want to select men, I can double click gender, I can click the equal sign, and I can double click, or excuse me, I can set the value that I want to pick the gender that I care about. Because I want to pick men for the first sample, I'll say gender equal 1, and I click the little add button here to get the 1 value up here. You can also just type it in, and I hit OK. Now this first sample is sleep for men for gender equal 1. Now if I want to make my second sample, I selecting sleep again, because that's the thing we're comparing, and I'm just going to type this in. You can type in, if you know your variables and you know these categories, you can type in the logic statement to select the category you want. So now I'm comparing men's sleep hours to female sleep hours. And remember this thing about pool or unpooled variances and what assumption to make? Here's where this comes in. The default is to say that the variances are the same from each of these populations. That can be a big assumption to make, so we're just going to uncheck that. And what am I doing with this question? Well, I wanted to estimate what the size of the mean difference is, so I'm going to make a confidence interval, and we'll set it at the 95% level. I hit compute, and I'm done. That's it. So since we did males minus females, 1 minus 2, what this is saying is that here's my lower limit, here's my upper limit on my 95% confidence interval. What it's saying is I'm 95% confident that males in this population sleep an average of less than 0.823 to more than 0.045 hours than females in this population. And just to give you an example of how complicated the degrees of freedom calculations can get, right there, 30. That's pretty wonky, right? There's a special formula that went in to do that, so you don't need to worry too much about that. And again, that conclusion is right here, 95% confident, 0.82 hours less, 0.04 hours more. And really, there's not much more to say about if you want to do the hypothesis test that they're different. So let's say that we want to ask, are these 2 sleep hour populations different from each other on average? I just go back into StatCrunch. I'm just going to use what I have here and edit it. I have my 2 samples, and I say do a hypothesis test, and my null value is 0. I hit compute. I get a p-value of 0.07. That's above 0.05, which you should have guessed because it's inside the interval. And I conclude that on average, we do not have evidence that there's a difference in sleep hours between these populations. And that is it.